of other, you can indirectly, through some sort of experiment, you could use one of those expensive electro-optical modulators, rotate these things 45 degrees and put them through a horizontal vertical filter. Or you can just rotate your filter 45 degrees, a little cheaper. But they are physically distinguishable through some kind of experiment. Another example of quantum mechanics with the naked eye, my favorite, is the Mach Zehnder interferometer. So here, these particles, now the only cheat here, the main cheat here anyway, is that this is a continuous beam of light. Now in theory, and in practice, but it's not very exciting to see one particle of light because you can't really see it, if you could slow this down to one particle of light at a time. Click, 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 click. And this particle goes through what's called the beam splitter. Half of the time it goes through, half of the time it's reflected. It goes through this beam splitter, half of the time it goes through, half of the time it's reflected. So the particles going out of this photon source can take one of four paths. This one, and I forget which one anyway, there's four paths. Okay? And they all occur with probability a quarter. Well, actually, that's not what I mean. They all occur with probability amplitude, that's square root of a quarter. And this path occurs with probability amplitude minus a half. The square root of a quarter is half. This path occurs probability minus a half. This one with probability a half. This one with probability a half. And this one with probability half. Sorry if I missed, but... So there's two ways to get here. And normally with probabilities, like there's many different, when Nate Silver computes Toronto Blue Jays, I think they want an 11 or 15% chance of winning the World Series. There's many ways that could happen. Obviously they have to beat Texas. But then, it depends who the winners of that next game are and the next game, and then, there's many different paths. And they each have some probability of happening, and if you add up all those probabilities, you get the 11 or 15% figure. That's the current estimate, say. Same thing happens if you don't look. If you're not looking to see which path is taken by the photon, you add up the amplitudes. You don't add up the probabilities, you add up those quantum amplitudes, which can be negative. So if you don't look to see which way, if you're always looking at where the photon is going, then it is indeed probability a quarter for each of the paths. So two of the paths go here, so it's a quarter plus a quarter, 50% chance of hitting this. Two of the paths end up here, 50% chance of ending up here. But if you don't look at it, then you don't add up the probabilities, you add up the amplitudes. So you get the chance of coming here, ending up here is half minus a half. So it vanishes. It occurs two different ways. Their amplitudes are the opposites of each other, so this event never occurs. That's why you don't see any red beam here. So beautiful quantum explanation for this great experiment. Now, we can extend this beyond 1 bit to say 3 bits or hundreds or millions of bits, but let's look at 3 bits. There's 8 ways you can configure 3 bits. They could all be 0, 0, 0, 0, 0, 0, 1, etc., 1, 1, 1. This particular superposition, linear combination, there's 3 events that never happen, that aren't there at all. There's one, this is the most likely event, right? The 0.875 squared probability of 1, 0, 0. So if you were to look at these atoms, you'd most likely measure this. The next most likely event is this one, and so on. And the aim of a quantum algorithm, quantum computer, so what you do is you shine lasers on these atoms. So this is, again, this is just 3 atoms. It looks like, 24 atoms, but it's just 3. I just have this very long-winded way of trying to explain the state of these 3 atoms. So I just shine light on the first atom, say that flips. If you shine a light with the right laser frequency and intensity, 0 will get mapped to 1 and 1 gets mapped to 0. So if you shine that light here, for example, you'll flip the first bits. So now you'll have a 0.401 amplitude for 011, and so on. But you could also do half of that pulse and map this 0 into a 0 plus 1. And what you'll notice is there's many paths. These strings are branching out. They always go to one of the 8 strings, but you can go to all the one of the 8 strings in countless different ways as you do more and more gates, what we call logic gates, or interactions, more laser pulses on these atoms. And if you want to know, after this long computation, shining lasers on these atoms, what's the likelihood of seeing 0, 0, 0, you have to look at all the amplitudes of all the paths that lead you to 0, 0, 0, add them up, and then again, the things could add and subtract. When things cancel out, we call that destructive interference. And when they add up constructively, when you have a bunch of positive amplitudes adding up, or a bunch of negative amplitudes adding up, we don't care about the final sign, we just care about the size of the number, because we're going to square it anyway. Right? That's called the constructive interference. Quantum algorithmics is all about choreographing constructive interference on the answer to your problem, and destructive interference on the non-answers to your problem, the stuff you don't care about. So you hopefully, if this is a good algorithm, then 1, 0, 0 is the answer to your question. And it's actually very hard to choreograph constructive interference, to choreograph these quantum algorithms. Now, another point I want to make is, so I said this is really just 3 atoms, but it's kind of a pain. I have to keep track of 8 numbers. And then if I have 10 atoms, I need to keep track of 1,000 numbers. And 40 atoms, I need to keep track of 1 trillion numbers. I have to keep track of the amplitudes of every possible configuration. So it quickly explodes. This mechanism for trying to classically simulate a quantum computer, a bunch of quantum bits, also known as qubits, this method is infeasible once you get to 100 or more bits. Again, but that's not to suggest you have the equivalent power of trillions and trillions of classical computers. You don't. But in some very special way, you are able to probe all of these configurations. Right? So what are these good quantum computers good for? It's not a free lunch. It's not like having 8 3-bit computers. For some problems, it is. For some very specific problems, it does appear to be. But in general, it's not what it is. What they're good for is for finding global patterns, global properties. What I sometimes call seeing the forest without actually observing the trees. I don't mean coarse-grained view of the trees. I mean you have very precise properties of the forest, but you don't know anything about any of the trees. How can you do that? Well, quantum mechanics allows that. So what do I mean by global property anyway? But here's a math problem. Here's a sequence: 34, 12, 54, 38, 57, 34, 12, 54, 38, 57, 34, 12. It repeats. Every 5 numbers, it starts all over again. Now, the first 5 numbers are distinct. Like within the period, it's distinct, but then it repeats. That's a well-defined math problem. What's the period of this sequence? Let's make it a little harder. Let's suppose a sequence of numbers, so these are 128-bit numbers. So, right, 16 bytes, binary, whatever the physical encoding is, we don't care. So the number 1, this would also be encoded in binary in the computer, gets mapped to this pattern. The number 2 gets mapped to some other completely different pattern. The number 3 gets mapped to some other completely different pattern, and so on, and so on, and so on. 729 trillion, 672 million, 729 billion, 672 million, 482,463 gets mapped to yet another distinct pattern. And then 729 billion, et cetera, and 64 gets mapped to, right? I know I can see it. You've noticed that's exactly the same pattern that 1 got mapped to. And then that's the cycle, right? And then this is the same as what 2 got mapped to, and so on. So I'm guessing, I'm getting the sense that you profoundly don't care about what those precise patterns were. Right? But if I wanted to classically, on a classical computer, find that period, The naive way is just to do 700 and whatever billion different calculations. You collect all this garbage data you couldn't possibly care about until you see a pattern. It takes up a lot of memory. There's actually more clever algorithms that take square root of that many steps, roughly 1 million calculations, and they'll see a collision, they'll see the same pattern. It's like the birthday surprise paradox. If you take about 20-some people in this room, there's high probability that they have the same birthday. 2 people have the same birthday. So there's a square root, well-known square root method in computer science and cryptography. But that's still a lot of garbage information you don't care about. You just want to know the period. What a quantum computer allows you to do is, you take the 128 bits for the answer. You take about 100 bits or so to encode 1, 2, the n, the number n. You compute the nth pattern. But you do it, you prepare you prepare a combination of all the input numbers, which is an easy thing to do. You have, say, 100 quantum bits. You just make each of them into one of that square root 0 plus square root 1 state. So it's really easy. You just quantumly flip each bit. Those input bits, the bits that encode, the 2 and the 1 and so on, it's very easy to prepare them in a combination of all the possible patterns with a small number of steps. Then you compute the bit pattern. You just do that one computation on this roughly 200 bits. And what you physically embody is, 1, the first pattern, 2, the second pattern, 3, the third pattern, n, etc., 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 n, the nth pattern. In those small numbers, in just that one quantum computer. It's somehow in all of those states at the same time, whatever that means. Now, don't look at it. If you look at it, all it does is it effectively collapses to one of those states, and all you get is some random input n and the nth pattern, which you don't need a quantum computer to do. Right? You just randomly pick an n and compute the nth pattern in that case. Don't look at it. What you do is you kind of jiggle it and see how it jiggles back. And you do what we call a quantum Fourier transform, which is very much like the Fourier transform if you're an engineer or you're into signal processing and so on. They're very useful for finding patterns and periodicities in signals. So you do actually have what Peter Shor discovered is a very simple sequence of pulses on these bits, these quantum bits. First, this Fourier transform type thing. It's essentially the equivalent of when we went, instead of looking at them, don't look at that photon this way, look at it this way. Okay. That's the 1-bit version. The 128 or 100-bit version is called the quantum Fourier transform. But you're looking at it in a different way. Then what you see is a number which encodes the inverse of the period. Actually, an integer multiple of the inverse period. So you'll either see something that's an approximation of 1 over this large number, or 27 over this large number, some integer over this number. And if you have a good enough approximation of a fraction, there's a well-known method in number theory called the continued fractions algorithm that spits out the fraction. It cleans up the noise. With a denominator, you pick a denominator size. It'll give you a sequence of fractions that approximate that number, and ultimately you will find that denominator with high probability. So it'll spit out essentially the period. And you only need one. You could do if you do this once, you have a good chance of finding it. If you do it 2 or 3 times, your chances get really close to 1. So with a very small number of steps, you don't have to do 729 billion or square root of 729 billion steps. You just do 1 or 2 or 3 quantum glimpses at this data, and it will spit out the period. But if somebody asks you, but what was the 3rd or the 4th or the 5th pattern, you'll have no clue, because you didn't look at it. You couldn't have looked at it. So you get this global property, but you don't learn any of the details. Now, I'm sensing that nobody in the room really cares about finding the period, of large sequences. Not quite nobody. I see at least one famous cryptographer, Ron Mullen here in the second row, who understands very well what the implications of an efficient period finding algorithm is, and I'll tell you a bit more about that later. But for most people, it's not that interesting. I'm demonstrating this. This is not so much an interesting, application, but I'm trying to get a sense of what I mean by a global pattern. The applications that would be interesting to most people include simulating quantum materials, right? The kinds of materials that our colleague, Duncan Haldane at Princeton, who's a distinguished visiting research chair here at Perimeter, that he just won the Nobel Prize for on Monday, along with his two other colleagues. They're studying these quantum materials, which have these, offer these new phases of matter, basically. Phase of matter, you have gases and liquids and solids, but quantum mechanics at low temperatures offers entirely new phases of matter that don't depend on temperature, but some other parameters. And if you want to study these materials, it's really, really hard, because you have to study them in a quantum mechanical way. You have to look at how all these configurations, when you want to say what's the probability that after a certain amount of time you end up with this configuration, or this is just an artist, this is an fictitious thing, but that you get a 1 here, or that you get a certain pattern. You have to explore all the ways to get that result, add up the amplitudes, pluses and minuses, and so on. It's a really hard calculation. Quantum computer can help with some of these questions about quantum materials. Or if you want to study a chemical reaction at the quantum mechanical level, a quantum computer can help. Another example for how a quantum computer can help is searching and optimizing, so-called needle in a haystack problems. Right? So in optimization, and I see famous optimizers in the audience too. We're not literally looking for a needle in a haystack. This is a metaphor for there's a solution to a math problem, something very important. You're trying to optimally allocate a resource. You're trying to design a building to be earthquake-proof. You have money for so many dampers. How should you configure those dampers to maximally protect you against earthquakes? Now, you can try tons. There's countless, exponentially many configurations. Given a configuration, there's models to test how earthquake-proof it is, but you don't have time to go through all of them. Right? So these are the kinds of questions we look for that optimizers in industry try to solve. Or there's other problems where, if I give you the answer, you can check it, but good luck trying to find it. If there's no structure, the best thing we can often do is just try all the possibilities until you hopefully find that answer. So these, all these pieces of hay or this, blue needle that I'm not looking for represent are the wrong answers or the non-optimal answers. And this needle is the optimal answer that I'm really looking for. Let's suppose there's just 1 million possible answers. Usually there's many, many more, but let's say 1 million. An obvious thing to do is just randomly guess a solution. And you're probably not going to find it. And try again and again and again about 1 million times, and then you'll probably find that needle. But remember, if you quantumly just guess a random solution, a random place, a random configuration of 1 million possible configurations, 1 million possible ways you can, if you're trying to do airline scheduling or scheduling classes at a university, you look at all those configurations. Pick one at random, right? But quantumly pick one at random. Have your quantum computer prepare them all at the same time. Again, don't look at it, because if you look at it, you're just going to collapse to a random guess. Remember, quantumly, what's going on underneath is these all exist with amplitude square root of 1 in 1 million, which is 1 in 1,000, 1 over 1,000, plus or minus. So this idea that Love Grover at AT&T Bell Labs came up with was essentially saying, don't look, make a quantum guess, but don't look at it. You got the answer with amplitude 1 in 1,000. Then make another quantum guess, but don't look at it either. And another one and another one and another one. If you do it, and this is not an easy algorithm to design, But effectively what he came up with was a way, with about 1,000 quantum guesses, without looking at them, he boosted this amplitude to be close to 1, either 1 or minus 1. And then you look at it. Because by then you've boosted that amplitude to be close to 1, and 1 squared is 1, right? Or minus squared is 1. And you solve that optimization problem with just 1,000 looks instead of 1,000,000 looks. Or if it's a 1 in a trillion problem, you only need about 1,000,000 looks instead of 1,000,000,000 looks. So there's a host of there's a host of application areas for quantum searching and optimization that take advantage of what's going on under the hood in quantum mechanics and of these quantum features that I've told you a bit about. There's another interesting feature of quantum mechanics known as, well, which I'm describing as eavesdropper detection. It's related to the Heisenberg uncertainty principle. So earlier, I told you I could send light to you in one of 4 possible states. Can you perfectly distinguish all 4 of those states? If I don't tell you which of those 4 I'm choosing, you can try. If you put your filter up this way, you'll be able to tell. You can perfectly distinguish, say, horizontal and vertical, but you'll totally randomize the diagonal. If you put it diagonally, you'll be able to perfectly guess the diagonals, but you'll totally randomize the horizontals and verticals. And you can try everything in between. There's always something that you're going to mess. You can either mess up 2 things a lot and a couple things not at all, but you'll mess up everything. Or you'll mess up everything a little bit. There's a minimum amount of disturbance, no matter how you slice it. So if I send one of these 4